Welcome to today's paper reading. Today's paper is titled, ReMamba, Equip Mamba with Effective Long Sequence Modeling. This paper was published on the AR14 preprint by Danlong Yuan and colleagues from Wang Institute of Computer Technology, Peking University, and Meituan. The Mamba architecture excels in short context NLP tasks but struggles with long contexts compared to transformer models. This study addresses the long context efficiency issues of Mamba models by introducing ReMamba. ReMamba enhances Mamba's long context comprehension through selective compression and a two-stage re-forward process, with minimal additional inference costs. Experimental results show ReMamba improves performance by 3.2 points on the LongBench benchmark and 1.6 points on L-Eval, nearly matching the performance of same-size transformer models. The introduction of Mamba models addresses the significant challenges faced by transformers in handling long texts, primarily due to their quadratic computational demands and linear memory costs. Mamba models offer a solution with linear time complexity and constant memory demands during inference, eliminating the need for positional encoding. However, Mamba's performance on long context tasks is not as expected, prompting the development of ReMamba. ReMamba improves long context performance by selecting the top K hidden states and incorporating them into the state space, resulting in minimal additional computational overhead and significant performance improvements on benchmarks. Figure 1 compares the performance of pre-trained Mamba models and transformers of the same size across speed, short context, and long context tasks. Speed is evaluated under conditions of 6K input tokens and 1K output tokens. The short scores represent the average accuracy across 6 tasks: Huishuai, Pika, Archi, ArcC, Wino Grande, and OpenBook QA, as evaluated within the LM evaluation harness. The long scores correspond to the average scores on the LongBench benchmark, with all LongBench evaluations using a maximum token length of 2K to match the model's training configurations. The Mamba architecture is rooted in state space models, which draw inspiration from classical continuous dynamical systems. These models use a diagonal structure for the state transition matrix A to efficiently compute state transformations. In the context of Mamba, the state transition matrix A and input coefficient matrix B are made to dynamically depend on inputs, enhancing the model's expressiveness and flexibility. This is achieved through the use of the soft plus function and multiple space projection operations. Additionally, Mamba 2 introduces a new state-space duality framework that simplifies the structured matrix A further into a scalar times identity structure, enabling faster training and larger state sizes, while maintaining connections to attention mechanisms. The methodology of ReMamba is divided into 2 main stages. In the first stage, known as selective compression, 3 feed-forward networks are used to determine the significance of hidden states from Mamba's final layer. These hidden states are selected based on their importance scores, and a compression ratio ρ is applied to compress the selected context into K hidden representations. The top K hidden states are then selected based on their importance scores. In the second stage, called selective adaptation, the non-differentiability issue of top K selection is addressed by integrating importance scores into the selective mechanisms of the Mamba model. This stage also involves training modifications to optimize the newly introduced parameters within the selective compression mechanism. Figure 2 illustrates the ReMamba architecture, focusing on the selective compression and adaptation stages. In stage 1, the model selects the top K hidden states from the last layer based on their importance scores, calculated using the last hidden state HL. These selected states are then integrated into the Mamba's selective mechanism in stage 2. The compression ratio ρ and the relative range S, E, are key parameters that determine the extent of selective compression. This approach aims to improve long context performance by focusing on crucial information and reducing state space updates. The experiments involve preparing a substantial corpus of long context data by leveraging the OpenORCA dataset and LongAlpaca 12K. This process yields approximately 200,000 long context training examples and incorporates 300,000 standard instances from OpenORCA. The baseline Mamba 2.8b model and the ReMamba model are fine-tuned using LoRa with the same hyperparameter settings, along with a Llama 2-3b model for reference. Given the positional encoding limit of Llama 2-3b, fine-tuning is conducted with data truncated to 2K tokens. Evaluations are performed on the LongBench and L-Eval benchmarks, revealing that the ReMamba model outperforms the Mamba baseline, and the Llama 2-3b model performs best with a 2K token limit. Table 1 presents the performance metrics of various models on the English branch of LongBench. The models evaluated include Llama 2-3b Mamba and ReMamba. Key metrics such as WikiMQA, GovReport, and HotpotQA are used to assess performance. Notably, Mamba and ReMamba are tested with a maximum token length of 6K, while Llama 2-3b is limited to 2K due to positional encoding constraints. The table also differentiates between pre-trained, and fine-tuned SFT models. Table 2 presents the performance metrics of various models on the closed-ended tasks of L-Eval. The table highlights the maximum token lengths used for evaluation, distinguishing between fine-tuned and pre-trained models. Notably, Mamba and ReMamba models are evaluated at their training configuration's maximum length of 6K tokens, while Llama 2-3b is limited to 2K tokens due to positional encoding constraints. The results indicate a 1.64 average score improvement for ReMamba over the SFT Mamba baseline, showcasing the effectiveness of the fine-tuning process. In this section, we discuss the performance of our ReMamba model across varying input lengths. Our model consistently outperforms the baseline Mamba model, with the performance gap increasing as the context length grows. ReMamba extends the efficient context length to 6K tokens, compared to 4K for the baseline. Additionally, our model introduces only a single additional forward pass during inference, resulting in no additional memory consumption and maintaining speed comparable to the original baseline. We also verified the applicability of our method to Mamba 2, showing improved performance. An ablation study confirms the effectiveness of our introduced modules, and our model demonstrates robustness to variations in hyperparameters. Table 3 presents the performance comparisons of LongBench English branch on Mamba 2. It details the scores for pre-trained Mamba 2 pre, fine-tuned Mamba 2 SFT, and our model, ReMamba 2 SFT, all under a 6K max length setting. Notably, ReMamba 2 SFT demonstrates improved performance across various metrics, highlighting its effectiveness. Figure 3 illustrates the average scores on LongBench for varying maximum lengths from 2K to 9K tokens. The pre indicates pre-trained models, while SFT indicates fine-tuned models. The performance of Llama 2-3b SFT and Llama 2-3b pre is included for reference, constrained to a maximum length of 2K due to positional encoding issues. Notably, ReMamba consistently outperforms the baseline Mamba model across all tested context lengths. The performance gap between ReMamba and the baseline widens as the context length increases, and ReMamba extends the efficient context length to 6K tokens, compared to 4K tokens for the fine-tuned Mamba baseline. Figure 4 presents the average scores on L-Eval across varying maximum input lengths from 2K to 9K tokens. The performance of Llama 2-3b SFT and Llama 2-3b pre is included for comparative reference. This figure highlights the model's performance under different context lengths, providing insights into its robustness and effectiveness in handling longer sequences. Table 4 showcases the performance of various model variants on the LongBench dataset. The ReMamba model type, which is our optimal model, demonstrates the highest average score. The middle type models, where the parameter S is non-zero, show a noticeable performance degradation compared to the ReMamba. The special model variant, which compresses the entire prompt using a compression ratio of rho equals 0.009 and appends the compressed hidden states to the end of the original prompt in the second stage, performs even worse than the fine-tuned Mamba baseline. Figure 5 presents an ablation study focusing on the average scores obtained from the LongBench benchmark across varying maximum input lengths, ranging from 2K to 9K tokens. The study compares different selection methods against a fine-tuned Mamba baseline, denoted as Mamba, SFT. The methods evaluated include fixed select for fixed selection, random select for random selection, and multiplicative select for multiplicative selection. This analysis aims to highlight the performance differences and the effectiveness of each selection method in handling longer input sequences. Figure 7 illustrates the robustness of the ReMamba model by varying the hyperparameters p and rho. The row labels represent the relative ratio of the prompt to be compressed, corresponding to parameter p, while the column labels indicate the compression ratio, corresponding to parameter rho. The parameter s is fixed at 0 for these experiments. The figure highlights the performance degradation observed when compression is applied in the middle of the sequence, as opposed to from the start. In this study, the authors introduce ReMamba, a novel approach designed to address the long context efficiency challenges posed by Mamba models. ReMamba compresses and selectively preserves critical information during an initial forward pass, integrating this compressed information into the state space during a second forward pass. This method incurs minimal computational overhead, while substantially enhancing Mamba's long context performance. The degradation observed in Mamba models can be attributed to the disruption caused to the causal language modeling nature of the model. When compressed information is integrated into the initial position, it can proceed without modification, treating the compressed data as a specialized non-zero initial state. Conversely, inserting compressed hidden states as tokens within the sequence disrupts the causal language modeling paradigm, leading to performance degradation. Among the tested models, the variant that appends compressed hidden states to the end of the original prompt exhibits the most pronounced negative impact due to the significant disruption of the model's expected input structure. Despite these challenges, the model that compresses in the middle still outperforms the fine-tuned Mamba baseline, indicating a promising avenue for advancing the Mamba model family. Figure 6 presents a comparison of the speed performance of different models in terms of tokens processed per second. The models evaluated include ReMamba, Mamba, and the vanilla transformer model Llama 2-3b. The input and output lengths for each model are fixed at 1024 tokens. The speed metric, measured in tokens per second, provides insights into the efficiency of each model during inference. This comparison highlights the relative performance of ReMamba, which maintains a significant speed advantage over traditional transformers, despite introducing only a single additional forward pass during inference. Thank you for watching.